go ahead.
Okay, so okay, now I will discuss about chapter 7 about 3 helium-4 helium dilution refrigerator. So the first is as we already learned in the previous chapter that the temperature range accessible with liquid helium-4 is about 4.2 Kelvin and can be lower up to 1.3 Kelvin. So this is the minimum temperature of different refrigeration techniques. And we can make a lower temperature up to 0.3 Kelvin by using liquid helium-3 as we discussed in previous chapter. So in order to reach the lower temperature, London et al. Proposed new technique by mixing helium-3 and helium-4 based on an idea proposed by H. London about 10 years earlier. So instead of the using latent heat of evaporation to cool down, in this new technique, they use the heat of mixing helium 3 and helium 4 to obtain the low temperature. So then in 1955, the first helium 3 helium 4 refrigerator was built based on this principle, and could reach 0.2 Kelvin. This, and then for the next year, Neganov et al. Built the dilution refrigerator down to 25 millikelvin. So the helium-3 helium-4 refrigerator to be discussed in this chapter is the only continuous refrigerator for the temperature range below 0.3 Kelvin. And this book also mentioned that the complexity of helium-3 helium-4 refrigerator for the temperature range above 30 millikelvin is still comparable to the complexity of helium-3 cryostat. And we can modify 3 helium cryostat to helium-3 helium-4 refrigerator. But in order to extend the temperature about 15 millikelvin range, it can still be built in the laboratory. So if we want to build by ourselves and we need to reduce more temperature lower than 10 millikelvin, so lots of experience and manpower is necessary. But it is also time consuming. Maybe it doesn't say have more experience about this. And also this book also mentioned that nowadays commercial helium-3 helium-4 dilution refrigerator down to 4 millikelvin are available, but they are still expensive. I don't know the exact cost of this. So and the lowest temperature can be reached is also below 2 millikelvin, has been achieved by Frosty et al. So and the temperature range, as we know that the temperature range of the that accessible with the liquid helium-4 is about 4.2 until 1.3 Kelvin. So and we can reach the lower temperature by helium-3 refrigerator. So maybe we recall on the earlier discussion about the properties of helium-3 helium-4, why these things happens. So as we know that the physical properties of helium-3 and helium-4 is we see from this phase transition, uh, helium 4 is at the superfluid at around 2.17 Kelvin, and for helium 3, it is in the superfluid at the millikelvin range, millikelvin temperature range. It's different. And the next is about the oh yeah, also because helium 3 has the larger vapor pressure than helium 4, this is related to the cooling power. So we also have to consider about the cooling power. So helium 3 has a larger cooling power. Yeah, because larger vapor pressure means that the larger cooling power, as we know from previous equation. But we also know that the cooling power decrease exponentially with the decreasing of temperature, right? In the previous equation. Do you still remember? Okay. So because also 3 helium has a yes has a lower latent heat, and also they has larger specific heat. So helium 3 has larger as can be have larger heat reservoir compared to the helium 4, but it has smaller, yes, has smaller latent heat evaporation. So it means that it is very easy to evaporate. So we need to means that close gas handling, closed cycle is necessary. And then next, this is properties of the liquid mixture, helium 3 helium 4 mixture. So at the saturated vapor pressure here, saturated vapor pressure means that the exert pressure by the gas that produced by evaporation of the liquid inside the closed container. So when the equilibrium is achieved. So for instance, now in this case, if we have so before I go there, so this is the equation of concentration of helium 3 is denotes by X, and this is concentration of helium 4. So this one. Okay, so uh, yeah, for example, maybe we have this we have helium 3 helium 4 mixture at certain temperature and certain value of the helium 3 concentration. It is X. So if we cool down to lower and lower temperature, then we reach to the we have lambda line here, and when we reach the two-phase region here, so this is when we decrease the temperature, the concentration is still same from here to here. But when we reach this line, the two-phase region here, if we cool down to the lowest temperature, so when the 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 liquid in this shade area will separate to the two-phase, become two-phase. And for example, like this. So in this part, we have mixture of helium 3 and helium 4 with certain concentration. And when we go to this region, we will have two phase separates here and here. The first one is close to 1 x close to 1, and this is called uh, concentrate. Is I mean the solution which has rich of helium-3, and this part is the solution which have rich of helium-4. And because the density of helium-3 is large, is lower, so they will float at the top of the helium-4 rich concentration, like this. And also the temperature of the, if we goes to this area, the temperature of superfluid phase transition of helium-4 is depressed when we dilute the helium-4 with helium-3. And it the superfluidity of helium-4 also will disappear eventually for if we increase the concentration, and at the concentration of 60.7. Yes, so the fluidity will disappear. And if we go to the lower, this one, if we go to the lower temperature at the millikelvin range, surprisingly, we found that the rich helium-3, the concentration is equal to 1. It means that we have pure helium-3, but surprisingly in the helium-4 rich, we still have helium-3 concentration about 6.6%. So this is I mean at this temperature range, they have finite solubility. This is the one characteristic of the helium-3 helium-4 mixture. So, and the next, this is the equation of the limiting concentration. It means that at the very low temperature, close to zero, the concentration X concentration of, yes, helium-3 and helium-4 is constant. So, and also they mentioned that the solubility of helium-3 and helium-4 can be increased to up to 9.5%. Only at this 50 millikelvin temperature, we can increase the solubility by apply pressure and raising the pressure up to 10 bar. Yeah, here. So this is the so this this I mean these properties uh, can be used to cooling cooling process, for cooling process in the helium-3 helium-4 refrigerator. So the cooling process is achieved by transferring helium-3 from the pure at the top part we have pure, almost pure helium-3 phase to the dilute phase. Dilute phase means that the the concentration lower concentration of helium-3. So it is almost similar with the cooling process at the helium-4. When we have helium-4, we when we want to cool down lower than its boiling temperature, we evaporate, we pump out the evaporation, yes, the evaporate gas inside. Then we can cool down by pumping. Yeah, means for this, in this case, we just transfer the helium-3 from the, just change to the different concentration. So this is the if we know that the equation of cooling power of the cryoliquid is denoted by this equation. So then the okay, this way. So as we know from the previous chapter, we know that the cooling power. So the cooling power of the pure helium-3 is decreased exponentially. So if we lower the temperature, if we decrease the temperature, then oh no, as a decreasing temperature, the cooling power also decrease exponentially. Then they will have a limit of the temperatures range we can cool down. But for the mixed helium-3 helium-4 mixture, we have the temperature dependence of the cooling power is the weaker, not exponentially like helium-3. So it means that the cooling power does not decrease significantly as the decreasing temperature in helium-3 helium-4 mixture. So this we can take the advantage of this phenomena to get the lower temperature than the helium-3 can reach. So yeah, so I think I can discuss up to here because for 7.1.2 I didn't finish understanding yet, so sorry. Maybe that's that's all I think. Sorry.
Okay, what? Okay, sorry. Which section did you go? Okay, 1.11. 7.11 is okay. You went up to 7.11. Okay.
Please.
Phase diagram and solubility. Up to which section did you go? I'm sorry.
7.1.
7.1. Okay, okay, okay.
So because yeah, I didn't finish understanding 7.1.2. So
Okay,
I
yeah,
just
yeah, yeah. Okay, okay. That's okay. Any questions? And most important point to introduce the dilution fridge is yeah, to create low temperature 3He starts and just pumping the the vapor has some limitation. That's why we need a new mechanism. That's the most important reason to introduce 3He 4He for 3He 4He dilution fridge. And dilution fridge has a completely different cooling mechanism. But probably you will explain this next week. I don't know, or somebody else. Maybe somebody else. That's okay. Or if you want, you can do it.
okay.
I mean, that's
Uh,
up to you.
okay. I have question. So this books mentioned that commercial dilution refrigerator is so expensive, and how about in the ULT lab? Do you set up by yourself or by commercial one?
That's commercial one.
Oh,
But yeah, I didn't buy. I didn't buy myself.
I see.
Yeah, but it's like let's say $20 million yen. I mean, we have a huge one in the ULT lab, right? Two huge ones. I would say that probably 100 million yen.
$1 million.
For each, yes, I guess.
I see.
But if you make by yourself, it costs like less than 1 million yen, I would say. Yeah, I did when I was a master student. I made a cryostat with my advisor. I made a gas handling system by myself. Of course, my professor didn't pay my salary. Yeah, because yeah, graduate student labor is basically for free in that at that time. Without including my salary, then basically it's less than 1 million yen. Much less, I would say. Any other questions?
I have questions.
Yeah, you can ask to Erlina first.
Can you go to the last slide?
The last, okay. Ah, this one.
Yes. Basically, my question is about the. Have you read in the chapter 7 about the physical reasons why when we mix helium-3 and helium-4, we have better cooling power? Because if you see from this graph, it means that the latent heat is not easily approaching zero, and that what makes the mixture could go even lower to lower temperature. But the question is why the heat capacity, I mean the latent heat doesn't approach to zero as fast as helium-3.
You mean
Yeah,
cooling power?
Yes.
cooling power is equal to latent heat to enthalpy.
Enthalpy difference, I would say. Yeah.
Yeah, the difference of enthalpy. And that's my questions.
Maybe
Is there something different when they mix together?
Yes. Actually, I also wonder and still figure out the why, but maybe but I didn't understand yet. But maybe it is related to the quantum liquids of the helium, I think. But I don't know the exactly phenomena that things happen. Maybe I will find out and try to explain next week.
what? Yeah, or some other person, somebody
Okay.
can explain next week. I mean, maybe who is the next? Who is the next? Actually, who is the next? Actually, Wajima-kun and Makino-kun is working on basic bridge, so. Lenas is next one. Lenas may not be good person to study. So she's nothing to do with the leadership bridge. What about Makino-kun? You can continue to get. Maybe you two guys study together. I mean, basically that the question what Eric asking will be coming next week. Next step chapters basically. Yeah, most important point is the T-square dependence is most important. Yeah, that's why it doesn't disappear immediately.
Yes.
Next chapter, 7.1.2.
Yeah, and maybe 1 point. Yeah, okay, yeah, maybe 1.2, 1.3, maybe 1.4.
Oh.
Then basically you can understand what the mechanism of this dilution bridge. Basically. But you know basic mechanism already, right? No? I mean, you study with a student about 低温物理、低温の物理学、極低温の物理学。If you need, I can give you, I can borrow you the Japanese book.
No, I don't think I can read it.
I'm telling the Makino-kun. Maybe it will help.
7.1.3, 7.1.4.
Yeah, maybe you both guys working together, discussion. I mean, this is the most interesting part of the dilution bridge. Basically, yeah, quantum mechanics. Quantum statistics. Quantum mechanics statistics. Boson, fermion, such a thing.
Does the statistic change? Sensei?
Yeah, sure. That because boson. 4 helium is boson.
Boson.
3 helium is
Helium three.
fermion. That play a huge role for this. That's why, yeah, dilution bridge is basically like a quantum mechanical refrigerator. That's why it's quite interesting. Yeah, okay, good. Any other question? Comment? Right? Yeah, you can study another book. Yeah, we have another low temperature book, right? In the student office. That also explain, I think, dilution bridge. And maybe if you search, you can find many explanations about dilution bridge. And maybe you can study first the hand waving explanation.
And waving.
And then maybe easier to understand the more accurate explanation. Any other question, comment? No? Okay. So maybe we can finish. And I don't know what time Shimamura-san is ready, because he's teaching labo course now. So let's wait until he finish. But let's start at 5:30 as usual. Maybe you can tell us what you did this week. And whenever he comes, let him talk about the journal. The paper. Okay. Okay. So
Thank you.
Great.
bye-bye.